Dear friends, welcome to another brief video in which we introduce a new geophysical technique termed induced polarization. In practice, induced polarization is applied in parallel with the resistivity method, and as you will learn in this video, both techniques use the exact same measurement setup. However, they do provide complementary information about the subsurface, and this is why it's good to combine those two methods together. So the learning goals of this video are threefold. Number one, I would like you to understand the general geophysical context of the induced polarization method. We will define what's the parameter that this method is sensitive to, and this is the chargeability, and there are also phase lags between current source and the potential difference measured at the surface. This video will stay at this conceptual level. We will not develop models. What happens if the chargeability changes vertically? What happens if it changes laterally? This is outside the scope of this video, but it obviously can be done the same way it has been done for the resistivity method. And we'll finish this video with one example that shows clearly how it is useful to combine both resistivity mapping and induced polarization. Okay, in order to understand induced polarization, we definitely need to know what is a polarization in general. And for this, I use this sort of simplified picture here of an atom. This atom has a delocalized electron cloud that flies around a nucleus, and this nucleus is typically positively charged, containing a number of protons and neutrons. So if we look at this thing from afar, it's electrically neutral. It's not an ion or anything like that. However, if we now apply an electric field, and in this example this is done from left to right, then these electrons, they tend to move towards the positive end of this electric field, and the protons and neutrons, vice versa, would like to move to the negative end of this field. And the net effect of this is that this picture, which is totally spherically symmetric in this example, becomes polarized. Polarization means charge separation, and induced polarization means that this charge separation only occurs if an external field is applied. Once we remove that external field, this polarized, electrically polarized molecule will relax back to its unpolarized preferred condition. Okay, so induced polarization is the induced separation of charges over small distances. So this is not a current flow, it's just a separation of charges. And if we look at this in a slightly more macroscopic picture, you have a substance in here, many different molecules which have potential to be polarized. If we now apply an external field, in this example it's oriented from the top to the bottom or from the bottom to the top, then all those molecules will flip to have this electric dipole moment or the electric polarization aligned with the electric field lines, okay, because this is the way how charges orient themselves in an electric field. And now let's have a look at the net effect of this. So each individual little molecule here or little particle will orient itself, but you can always find pairs within the volume so that the net effect will cancel out. Okay, so in this example here, this positively charged end, you can combine it with the negatively charged end of the neighbor, and the net effect here will be zero unless you are close to the surfaces where you don't find these cancelling pairs, and so this will lead to a net, this example, net positive surface charge down here and a net negative surface charge down up here. Okay, and so what's the picture that goes along with that? In an electrical circuit kind of sense, it's the picture of a capacitor or Kondensator in German. Okay, a capacitor are essentially two, let's say, metal plates in an electrical circuit, and those plates can be charged with charges if an electric field is applied in the circuit. And we'll discuss this now in a little bit more detail. Okay, so obviously we are not electrical engineers. We're trying to be a geoscientist, or even better, maybe geophysicist. And so let's look at how this would be represented in the subsurface. Here's an extremely simplified view of the subsurface. So we have a some sort of a porous medium. It can be a sandstone or something in the critical zone. Okay, and this porous medium is characterized by a matrix and then a pore space, which is shown here in white. That pore space is filled with a pore fluid, and this pore fluid has many different ions. Sodium, chloride, phosphates, I don't know, many different ions in those fluids, depending on the setting that it's in. And if you apply an electrical field, those ions will be set into movement, okay, and induce a current flow along this upper part. And we are quite familiar with this. This type of current flow is the ohm style current flow, and there's a ohm resistance that will go along with that, okay? Induced polarization conceptually works in this lower branch, and there's now three mechanisms how you can polarize the subsurface that I've shown here. Any kind of metallic particles, for example in ore deposits or something like this, have a high possibility to become polarized in an external electric field. Okay, so this was actually where this method was first applied. However, it's also very sensitive to any kind of clay. Okay, clay with its negative surface charge and in combination with a pore fluid and an external electrical field has also a very large degree of polarizability. And last but not least, microbial activity. Okay, certain microbes and in a certain state of their cycle can also be susceptible to an electrical polarization, which is interesting for many fields in, let's say, microbiology. Okay, so those are only three important examples, but there are many others of materials that can become polarized in the subsurface if an external electric field is applied. Okay, polarization is a time-dependent mechanism. Okay, so if you apply an electric field, it takes some time for the charges to separate. And there are many different mechanisms of polarization. They can occur on an atomic level, okay, or they can occur on an ionic level, or they can occur around surfaces. And all of those have very different timescales, and they can range from seconds, milliseconds to maybe even many to timescales in the megahertz range. Okay, so very fast oscillations. And it's important to know that for the induced polarization method, we are in the comparatively low frequency. So we are in the slow time domain. Diffusion plays a role, and that is a slow process. And we don't go for now into these very high oscillations where things such as electromagnetic waves and ground penetrating radar would be relevant. Okay, so IP has a time variable component, but it's a relatively slow time variability. I guess that's the takeaway of this method here, of this slide. Okay, and we'll discuss this as we go along. Okay, so now the question is, how does induced polarization change the resistivity mapping? Okay, and the way we represent that is in this simplest possible electrical circuit that goes along with that. If you remember how we started the resistivity mapping, we started it with this upper circle here. We have a direct current source, a battery with a plus and a minus connection. Metal sticks into the surface, we use it as a current source, it will induce current flow, and we represent that current flow here in the upper branch flowing over an ohm style resistor. Okay, now we extend this method. What happens if we have polarizability in the subsurface? Okay, then we extend our electrical circuit, and we include also a capacitor. And here we have done this in a parallel way. Okay, could also be done in a serial way or in more complicated ways, but I found this to be the most instructive one. Okay, and in this kind of parallel setup, what's important to remember is that the current from our current source, IS, will split up into two currents, I1 and I2, and the sum of those two currents must be the total current, IS. Okay, this is the principle in parallel circuits, why the potential drop across those two branches is the same, the current is not. Okay, so this is the principle of any kind of parallel circuit. Okay, And how does a capacitor work in this kind of circuit? Okay, simplified picture. So we have two metal plates, and if we apply an external field, then charges will accumulate on those plates. Okay, and how many charges at which potential drop? That's a material property. Okay, it's essentially the degree of polarizability, and this is represented here with the capacitance C. Okay, so the capacitance C is given by the ratio of charges Q accumulated on the metal plate for a given potential drop U. All right, so what we would like to know here in order to kind of move ahead is what is the current flow. Okay, we are interested in the currents, and so for this I rearrange this equation. I isolate Q, which are the charges, and then I know that currents are nothing different than temporarily changing charge densities or charges or moving charges. And so in a simplified way, I take the temporal derivative, so the change of the charges, charge density, and this then corresponds directly or linearly to the change of the potential that is applied across this capacitor. Okay, so now we have a relationship for the current I flowing over a capacitor, and I just realized this should actually have the index 2, sorry, not 1. Okay, and so if you so wish, this is Ohm's law for a capacitor. Okay, so now we can kind of see how does this change our electrical circuit. We know that the total current, which we have good control on because it's at the surface, we have a current source, now splits up into these two branches. Okay, and so we this results in this equation here. And this equation, you know, at least the first part is one-to-one Ohm's law, meaning current is linearly related to potential via the resistance R. And now we extend this, okay? Now we also have a capacitor in the circuit, and so this makes this system slightly more complicated and most importantly, time dependent, okay? So now we have to think about times. We didn't really think about times in the resistivity method. We just switched on the systems and then moved on with the theory. Now we need to think of, okay, how does this time dependency actually play out? And the simplest way to do that is to look at the so-called step response, meaning we just switch on our system. So we induce the current in the subsurface, and then we measure the potential drop at the surface. And we ask ourselves, okay, what happens in this kind of step response where the potential is first 0, and then this is our initial condition, and then we see what happens, okay? And as it turns out, and I hope you recognize that, this is a differential equation, okay? What we would like to know is U, but we don't know U, we only know U and the temporal derivative of U. It is a classical differential equation. Here's our initial condition, okay? In the beginning, U is 0, fine. And so we can solve this equation. In fact, you will solve it in the exercises using separation of variables. Here's the solution, okay? This is the solution, how the potential drop measured at the surface in this simplified circle will change over time. And we can look at this formula a little bit before we actually sketch it out. Okay, so the first term, I, R, and then here's the 1, is Ohm's law. Nice, we know that from the resistivity method. And now Ohm's law is modified here by this exponential term, and we can look at two kind of limiting cases. If the exponential term is 1, meaning t is 0, so that's at the beginning, okay, then this entire thing here will be 0, and the potential will be 0. That's our initial condition, okay? And then there's other things. For example, if C is extremely large, then this value here becomes relatively small, meaning that the entire value is relatively large, meaning that the capacitance is more important. Okay, I mean, that was kind of silly. So let's sketch this function out. So on the y-axis, we have potential U. X-axis, we have time t. And I visualized this function here, okay? And it shows what it's supposed to show. At the beginning, the potential is 0, but then immediately it responds. It starts ramping up. And for very, very large times, the potential will be constant. In fact, it will be IS times R, we will be in Ohm's law regime. Okay? So what does this mean? It means for very large times, if we switch on a current source, then at some stage, everything in the subsurface is completely polarized. We cannot stuff more charges on the capacitor, so there's no current flow along the second branch of our electrical circuit, and everything goes via the resistance R. So this is then the resistivity mapping method, which operates over here. Okay? The induced polarization method deals with the spin up here, with the charging of the little capacitors in the subsurface, with the charging of the energy that we put into the subsurface. Okay? So here again is this limiting case. And now we can define a geophysical parameter that the induced polarization is sensitive to. And it is the integral over this spin-up curve. Okay? So again, limiting cases. If the spin-up curve is very, very small, okay, so meaning if this time constant 1 over RC is not very relevant, and we come very, very quickly to this Ohm's case, then the chargeability will be small. Vice versa, if the second term is very, very important, then we have a large area to integrate over, then the chargeability is important. Okay, so this is the definition of the parameter that the induced polarization method is sensitive to. It's the chargeability, meaning the integral over the temporal change of the potential difference that we measure at the surface. The more time lag, the more important the chargeability. Okay, this effect will not only occur during switch on, it will also occur during switch off. Okay, so that means if polarization is relevant and we switch off our current source, the readings at the resistivity meter will not be zero immediately. They will decay. This the induced polarization in the subsurface will relax. It will go back to its original state. Finally, the electric field is removed. So current flows into the opposite sense, and we will still measure this potential drop, this relaxation, even though the current source is switched off. Okay? So it's both. During charging and during decharging, we will measure the chargeability, and ideally, in an ideal circuit, those two should be, the chargeability should be the same in both cases, okay? In reality, it may not, and there's different ways how you can define this metric, but for now, that is good enough, okay? So knowing this, maybe an interesting question would be, what happens if I change the time scales of the switch on and switch off? Or, in other words, what happens if I reverse the polarity of this current source more rapidly? Can I gain additional information? How will this play out in the system? And this is what we will discuss in the following, okay? And we use the same principles, okay? It's the same, everything is the same electrical circuit, a same split of currents. The only thing that we change now is our current source. It's not a direct current source anymore. It's an alternating current source, and we represent that with a complex exponential. So a complex exponential is a nice way of representing sinusoidal currents. I hope you are familiar with that. If not, do not hesitate to ask us, okay? Importantly, in this video, the complex number is represented with J and not I, and the only reason for that is that we don't mix it up with all these I's, which are the currents, and not the imaginary number, okay? So this is the case if we apply an alternating current at the surface, and remember it's a lower frequency, so this omega is maybe in the kilohertz range, okay, thousands oscillations per second, which is comparatively slow, okay, comparatively slow, so no effects of electromagnetic waves or anything like that. It's just an oscillating current source, okay. So going back to our differential equation, here's U, here's the U dt, this is Ohm, this is the capacitor, and what changes now is that we don't have a constant current source, but we have a time variable current source, okay? So it's a new differential equation, but it's sort of related, and the ansatz that we do is that we say, okay, I don't know, if current varies sinusoidally, then the potential should as well. I think that is a reasonable assumption, and if we use that assumption, and we plug this one into the differential equation, then essentially nothing, not much happens here. But here we have to calculate the temporal derivative of an exponential. That is not too difficult. It results in this j omega term here, okay? And it's easily written down, but the meaning is maybe a bit opaque, because what we have now here is again a relationship between current and potential drop, sort of Ohm style, but the resistance slash resistivity is now complex, okay? And this is once kind of this extension from a real valued resistivity to a complex valued resistivity occurs. That is the transition zone where induced polarization becomes very relevant, okay? So can we maybe grasp some meaning out of this? Yeah, I think we can. And we just follow on using our mathematics of complex numbers. So this is essentially a complex number. So let's see where we go. Okay, I is now a complex number with a real part A and an imaginary part J times B. Okay, so you can imagine an imaginary number as a vector, okay, which has a direction and an angle, okay, and we can calculate the magnitude of this number using the essentially Pythagoras theorem that is here, okay, so no problem. But more importantly, we can calculate here this angle in the complex plane, phi, which would be the tan of the imaginary component over the real component. So imaginary component is omega times c, real component is 1 over r, so we do the ratio of those two, and so this gives us this omega c times r phase angle, okay? So what does this mean? Okay, what does especially this phase angle mean? So maybe we can just visualize this phase angle as a function of this omega c r product that's in there. And so this is the phase angle, and it has two important limits. One is the phase angle can be 0, and one is the phase angle can be pi half or 90 degrees. Yeah? Those are the same thing. So this is the limits that this phase angle can take. So let's see when those limits are reached. Okay, so let's have a look at when the phase angle is 90 degree. Essentially, that's the case when this product here is very large. For example, when the capacitance is excessively large. We have a hyper capacity to polarize the subsurface, okay? This means we can keep stacking charges on our capacitor, okay? And this capacitor will store the charges, and there will be an electric field going in the opposite sense to the external field, okay? And this means that the potential drop that we will measure at the surface and the current source, they will be out of phase, okay? So if the excuse me, if the current source is at its maximum, it's very high, just before the polarity reversal, then the potential drop will be at its opposite sense. It will be very low because there's a lot of charges on our capacitors prior to the reversal of the cycle, where we kind of decharge the capacitor and it goes in the other sense. I hope this is one way of visualizing this context. We can do another one if R is really, really large. Yeah? If R is really, really large, then there is obviously no way for the charges to go around the upper circle, okay, because R is so large, so it can only go via the capacitor, and it's only the capacitor that plays a role. And in the capacitor, it's the nature of the capacitor that current and potential are out of phase. Remember, current is I, and then it's linked to du dt, so it's the temporal derivative of the potential that actually plays a role in this charging of the capacitor. So we are again in this pi half regime, okay? If the phase shift is 0, for example, if resistance is very low, yeah, if we have a highly conductive media, then all the charges prefer to go along the upper branch. Just do the Ohm style, yeah? We don't want to waste energy in this capacitors kind of stuff. We just do the Ohm style. We are very good in the resistivity regime, and there will be no phase lag between current and potential drop, okay? So visualized in a different way in how we would measure it, okay? So remember, we measure the potential drop at the surface with our electrodes M and N, okay, and we induce the current at the battery, and now we are in this time variable regime. So the current that we induce is the blue curve, okay, and the potential drop that we measure, if capacitance is relevant, will be out of phase, meaning those two curves will not be in phase. So this is the resistivity method, but they will be out of phase, and the degree of how much they are out of phase, so the phase shift corresponds to the shift of those maxima here, the degree of how much they are out of phase depends on a number of things, but it definitely depends on the possibility of the material to polarize, okay, C. It also depends on the frequency, so higher frequencies are better for induced polarization, if you so wish, okay, give you a more induced polarization signal, but it also depends on the resistivity/resistance of the subsurface, okay? So interpretation is not fully straightforward, but there's some first order things that you can definitely take away from it and then develop the theory further if you need to do so, okay? So here's the setup of the resistivity method. We have current electrode A, current electrode B, we have potential electrode M and N. All of this we already have in our resistivity mapping, and we kind of get this effect of induced polarization for free, if you so wish, okay? So whenever you do a resistivity mapping, you essentially also do an induced polarization mapping, and this is commonly done. So these sources, these current sources of resistivity meters, they're typically switching their polarities in the kilohertz range to exactly capture this effect of induced polarization if induced polarization is relevant. If it is not relevant, you adjust in your resistivity case, which is also fine, okay? So summarize, IP and resistivity mapping are in parallel, I just said that, okay? But we get an additional parameter of the subsurface, not only the resistivity, but also the chargeability, okay? Which is a function of time, it's the resistance that kind of develops over time as we charge our capacitor on the subsurface or as particles and microbes and so on get polarized, okay? And we could now continue and develop a theory. Chargeability changes vertically, laterally, step changes, and so on and so on. And all of this is done in books. It's a very well-developed method, but we will close this method here, and I trust that you can go into more detail if you so wish, particularly the outcomings of spectral induced polarization, where you really investigate the frequency range, this omega, okay, changing omega, and then you see how the capacitance changes. This gives you quite a bit of information in the subsurface. But the interpretation is also more difficult. Okay? So have we achieved our learning goals? I don't know. I hope so. You definitely know now the principle of induced polarization. Okay? You know what it is. It measures the capacity of the subsurface to develop electrical dipoles, to become polarized, and we capture this effect in form of the chargeability, which is the integral over the spin-up. Okay? We can also quantify it in terms of phase lag if we apply alternating currents. Yeah? All of this is known. The only thing that's left to do is show one application. I'm always a little bit soft on applications because I usually face severe copyright infringements in these kind of videos, but thank you to Terrana Geophysics. It's a company here in Mössingen that does a lot of geophysical mappings for a long time, and they provided us with an example in Damascus where they did a resistivity survey. Okay, in fact, they did a resistivity tomography, meaning they were able to resolve the resistivity both laterally and vertically, and this is now shown here in this color codes. And the interpretation requires obviously some geophysical context, but here this is interpreted as some interbedding between different materials, sandy and silty sediments in this example. Okay, so now we look at the IP signal, the induced polarization signal of the exact same survey. Shown here is the inverted chargeability. Blue colors are high, purple colors are average, and the dark colors are essentially zero. And what sticks out in this IP signal is this very, very strong anomaly in the center of the profile, which was not that clear in the resistivity inversion. Okay, the resistivity inversion shows a little bit of something, but by far not as clear as the IP signal. And the solution to this problem is here that IP picks up a localized steel pipe in 3 meters depth. Okay, and this steel pipe has obviously a very large geophysical contrast in polarization, because all of a sudden you have all this metal. Obviously, this will also be represented in the resistivity signal, but not as clear, because everything conducts a little bit of current here, it seems. So the contrast between the surrounding material and the steel pipe is large, but it's maybe not as large, and the resistivity method also averages over comparatively large areas. But the contrast in the capacity of polarization in this example is very large, and that's why this IP signal here provides important complementary information that is not contained in the resistivity signal. Okay? Simply because sensitivities are different for different methods and different subsurface materials. Okay. This is one out of a gazillion examples, and we will see more of those when we meet each other in person. Now I encourage you to have a look at the exercises, to go back, to ponder a little bit about maybe imaginary number, phase differences, because this will come back again once we go to different methods such as electromagnetic induction. Okay, but for now, it's enough. Thank you very much for listening, and enjoy the rest of your day.